Right. Hi, everyone. Uh, the topic that we are considering today is physics behind the sensors. Um, this is a very, very interesting topic. Maybe you may be able to. I hope some of you eventually develop some future sensors. So this today's the lecture covers from classical sensors and the physics behind the sensors all the way through the future sensors. I know some of you have heard of quantum computing and quantum mechanism, quantum technologies, and also applications. That comes near to us in high speed. So eventually, sooner or later, we'll have high speed computing, and therefore the world will change quickly. What that means is that the current technology all needs to be migrated to computing, the quantum world. In other words, the currently NVIDIA becomes so popular and very strong in semiconductor industries. NVIDIA will disappear, believe it or not. So wait and see. All right, the sensors. Human has, I think, five sense or six, five, yeah, as shown on the slide. Human has a touch sensor, smell, hearing, taste, sight. Yeah, those five senses already given. Okay, so it depends, right? Some people might have very, very sensitive and strong senses, one sense, while the other may not be that good enough. But anyway, so our sensor is not working 24/7, right? And our sense, the quality of sensibility does not, it's not sustainable. At younger years, maybe good, but as the aging, the sense capabilities may are decreasing. Okay, so technology and engineering can develop ultimately many sensors in various frequency range. In the later slide, you may be able to see the spectrum of the wave frequencies. Then you may understand clearly more. It is a wide range. So for each different small range of that spectrum, where there is a sensors developed. IR sensors, infrared sensors has been developed and is very, very actively used. For example, night view goggles that may that is a very, very actively used many the real world the work area, particularly military or airplane. One of the open-ended the question that I asked you recently, we have quite a few airplane the accidents. One of those is that helicopter does not have that as compared to commercial airplanes. Not equipped with high fidelity and capability sensors. Therefore, at nighttime, helicopter pilot needs to view outside with the night vision goggle, that is IR vision goggles. But it has a pros and cons. With the night vision goggle, we may be able to see at night, but the accuracy is not really good enough if it is not really dark night. Okay, like in Potomac River in Washington, D.C., a week ago, something happens, then helicopter probably wear the night vision goggle or not. None of them are clearly found. But anyway, so lots of uncertainty remains in sensors. So accuracy of sensors is really, really important in the future technologies. So recently, the laser-based sensors, that is expensive. But if we need it in a high quality surveillance, then laser-based sensors are employed. That may be the reason that Tesla does not include the laser-based sensor, for example, LiDAR. Not many cars are equipping with that. All right. So definition of a sensor, that we looked at this last week. Let's recall once more. Sensor is a device that is to detect the event, environment, okay, and then provide an output. So there is a two different energy that we need to consider at each extreme end. From input end, we have input energy and output energy, of course. Output energy, if we want to use it in our electronic device, electronically process it, then that output energy should be electrical data. Input energy may vary, right? From chemical energy, from mechanical energy, from another types of electrical energy, another magnetic energy, all different kinds of energies may be considered, right? Then the key issue here is who can convert from one energy to electrical energy. That is a transducer. Transducer is more, that is a terminology historically used in electrical engineering, but now we may simply say that is a sensor. Examples of sensors. On the left column, you may see temperature sensor, light sensor, pressure, microphone, chemical sensor, motion sensors, more and more. Then input energy for temperature sensor, there is a heat. Transducer, what sensor needs to do is to thermal coupling and therefore maybe some convolution to electrical energy. That's what we see here. So it could be voltages, it could be some resistance. Now, the other portion that we need to do is that is the software developments. In software, in coding, that we need to interpret it, right? If that is 2.5 voltages, then we need to say what it is, right? Our interpretation needs to be coded in our development. That is a software developments. You guys also watched the news and some commentations about the series of airplane crashes in recent weeks. Many of the commentators brought up in current cyber physical world, cyber physical world. In the cyber, everything is a cyber physical world now. Airplane, there's a physical devices, but could be controlled, should be controlled in cyberspace. So cyber physical world, or right. There are two things that we need to consider: development and operations. Development and operations. For example, air traffic control tower. One, the cause of the Washington D.C. The airplane accident. One of the causes is the staffing issues in that air traffic controllers, right? Air traffic control, the staffs are insufficient. The government didn't put enough money for them to hire, and also that job itself is not easy job. That's so stressful, right? So human needs to at least sit in that control tower the five different range of frequencies they need to look up. They said VHF, UHF, low level frequencies, high level frequencies, all range of frequencies. Usually that air traffic control covers 5 different ranges of frequencies, because each airplanes may use different range of frequencies to communicate. So people that the staff needs to take in charge of receiving and transmitting those signals in certain range. But that particular time at that DC Reagan Airport, the air traffic control at that time, only 2 staff members are working, at least 5. And if frequency range, if there is a BG frequencies, then 2 people or more than those staffs needs to work. That is one of the reasons, right? So operation is at one end, that is the big issue, operation. At the same time, software. Is our software developed and deployed on that air traffic control tower sound and complete and strong enough? Yeah, that's another issue. Anyway, so operation and development, those 2 key pillars in good maintenance of cyber physical world. Okay, second row in this table, light sensor, in other words, photons. So electrical power needs to be needed. That third column, transducer, that is something, that is a real technologies, right? That each of those needs a lot of explanations, right? And all kinds of physics involved. Not only physics, but chemistry also. Why currently most of them are physics. But in the future, when the quantum computing is involved, then not anymore only physics, but the chemistry as well. Not only zeros and ones, but somewhere in between. Lots of gray areas needs to be considered. So it is not anymore electrical power. That is the current computers. Electrical power is needed, right? But quantum computing is not based on electrical power. It's not zeros and ones. It's not whether there is a current or no current. It's not like that. That is more like chemistries. So mixing two different chemical component can mix and therefore, depending upon the amount of the chemicals, it may have different outcomes, right? So it is not only zeros and ones. It is all varies unlimitedly, many. That is the quantum computing basis. All right, so I want to take a look at this, and then I'll move on. Now we need to think of two kinds of sensors, passive and active sensors. If it is a passive sensor, then sensor itself is passive. Therefore, sensor doesn't do anything. But object has something to emit. Okay? For example, human body, then we can say, hey, we have heat, right? Thermal amount. So that is emitted from our body. So sensor simply receive it and interpret it. That is a passive sensor. On the other hand, the active sensor, object is not always emits, and sensor does not need to something that is given from the object. Sensor needs to find out something else. Although object does not emit, we want to find out something from the objects. More active sensors. So sensor send out image, the energy first, and then there is a reflected energy. And your software needs to interpret it. So key difference between active sensor and passive sensor, I listed in that table. So energy emissions, active, then active sensor emits. Passive sensor only detect, only receive. For example, active sensors can include radar-based, LiDAR, sonar, infrared. Those are all active sensors. More powerful, more expensive sensors are now active. On the other hand, thermocouples, microphone, photodiode, classical sensors are all passive. If it is active, therefore, power needs to be consumed. Passive, very low, only portion when they receive sensors and there is some conversion process and needs power. So low power consumption on passive sensors. Cost, of course, differently. Functionality, I think active sensors can acquire sensor data in any sensors. Even if there is some obstacles, still possible. But passive, it depends on the environmental signals. Obstacles then cannot. Active sensors is the best to do some sensitive surveillance and monitoring, and if accurate data is needed, then active sensor should be used. On the other hand, otherwise, then the passive sensors. Example of active sensors, then radar sensors that emit radio wave, LiDAR sensors emits laser beams, sonar, it uses a sound wave, acoustic wave, like our human acoustic waves, something that you may hear, but not all, right? We don't hear all the sounds as our dog can, but human can hear more than, for example, snakes. Whales can hear a lot more under the sea, under the water. Human, we don't actually hear much if we are under the water, right? Right. I don't really hear much. Very, 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 very limited. The wave frequencies can be hearable. Infrared, that is another the wave, light wave that emits infrared lights. As I said, the infrared light is a little lower frequency than red light. Red light is the lowest frequency in the visible light. Light, then you can see it from the lower to a higher frequency, then the lower where there is a red color, highest, then purple. On this picture that you can see here, this is not something available currently, but this is possible that you can equip, for example, LiDAR on the roof of a car. Usually Google and Apple that runs this kind of a car to capture the street views, and that street views can be embedded in the map services. Therefore, you may see that kind of the car runs the streets here and there, right, all the time, with the cameras. This is a radar camera that spins, and then police car might have the radar signals on the car, and ultrasonic sensors. Ultrasonic sensors are also equipped with the recent version of Tesla. So ultrasonic and the camera together to improve, enhance the accuracy of the detections. Therefore, currently Tesla's full self-driving software packages becomes powerful, very, very powerful. Onboard unit camera, EMPS. The wheel encoder. There is a each wheel since I think 15 or 20 years in the United States. The tire needs to include tire pressure management systems, right? TPMS. That is a must. So that TPMS sends tire air pressure and send out to the central unit, which is available in a car. And then there is depending upon the car visualization, you may see unbalanced power pressure, tire air pressures. So I already explained this. Stimulus to senses. Acoustic sound may stimulate a sensor. What kind of acoustic stimulus? It could be amplitude, phase, polarizations, spectrum, wave velocities, or electric stimulus also possible to activate the sensors. It could be electric charge, electric current, electric potential, electric voltages, electric field, conductivity, permittivities. All those are some of the terminology in electrical engineering concept. Magnetic, same thing in electrical engineering. There is an electric field and electric flux and permeability. Optical is more like light. So optical has a wave. So wave has amplitude, phase, polarization, spectrum, velocities, reflections, and emit, and absorptions as well. Thermal, like heat, temperature. So thermal flux, specific heats. So those are the example that can stimulate senses. So in response to these kinds of stimulus, your sensor may start function. Mechanical, some position change. There's a mechanical stimulus. Accelerations, if you speed up or slow down quickly. And force, stress, pressure, strain, mass, density. Those are all mechanical stimulus based sensors are so popular, and each sensor may cost about $1 less or more or less. Very, very cheap, right? So you can consider one of those. So what is the sensor network that we are considering here? The bottom under in the slide, there is a target objects. So from the target objects, your project needs to send a sense, and that sensor data needs to be controlled. How you can control the sensor data? The first, you have to wire the sensor. Sensor has pins. Some sensor may have 2 pins. Some sensor may have 10 pins. If that is a very, very expensive cameras, then maybe 15 or 20.
Hi, Professor. Sorry, I'm late.
That's fine. You're taking 555?
Yes. My name is Edward. You can call me Edward.
The first time that we met, right?
Yeah. Previously, I cannot attend the class because I couldn't register for the class due to there's an academic holding on the system.
Okay, fine.
Thank you.
Okay, take a seat. So please find out some requirements of this class. We're now talking about sensor technologies. It may need this kind of the Raspberry Pi, and in the Raspberry Pi you need to the wire and connect it to this wiring. Through this wiring, that you need to connect it, your between sensor and your Raspberry Pi. What is your background, by the way?
Cybersecurity.
Here at Mercy?
No,
I see.
I
Do you have any knowledge about
I'm sorry.
the sensors?
Yeah, I know about sensor.
Okay, fine then. All right. And some of the calibration, if it needed, then you have the calibrations. For example, distance sensors, then no, not distance sensors, motion detection sensor, then there's a sensitivity of the motion needs to be calibrated, right? Depending upon that calibration, your sensor behaves differently. Okay, and then collecting the data, and if there is an action listing, then action needs to be taken. According to that action listed, then actuation is now needs to be taken. And transmitting, if you want to, not only the actuation, but if you want to send out the sensor data to the cloud server, then you need to transmit that. So we, in this class, we also use cloud server. You don't need to set up the cloud, but I will do. I will make some of the middleware available so you can use that middleware to communicate. We'll see that a little later. Okay, this is a slide that I was talking about. This is a spectrum of the frequencies. On the bottom of this, then you can see here 100 kilohertz, some of the frequencies, right? Or 10 gigahertz. We are talking about only this range is magnified like this. In real spectrum, it starts from 1 hertz to 10 to the 20 or 30 hertz frequencies. Some of this, I think this is this is microwave. What is our visible? Okay, this is a visible wavelength. Visible. Well, this ultraviolet. This is visible is somewhere here. Optical, electronic photos. Yeah, something that we can see. We now see the objects, environment, right, through our eyes. That is in this range. There are a lot of others that you cannot see, which is X-rays or gamma rays, all ionizing areas. If there's very high frequency, then it destroys your DNA. So your DNA may be damaged. Therefore, when you go to X-ray, then usually you need to protect your skin cells, right? Otherwise, your skin cell will die quickly because it has a high energy, high frequency, high energy. In visible range, under the sunshine, depending on people, our skin may be impacted, right? Some skin may not, some skin impacted so badly, even under the sun. Some of the microwave that is in this range. Within this microwave, our cell phone is running somewhere here, within this microwave. And under this microwave, then there's a radio frequencies. So AM, FM radios. So here, AM in this range. AM, FM radios. FM radios here, I think 100 megahertz. Somewhere 100 megahertz, that is FM. AM radios maybe kilohertz, right? So you may hear when you turn on your radio, then it says some kilohertz radio stations. Then that is usually AM, FM is megahertz. So VHF, UHF, remember that I was talking about the air traffic control tower that may receive a VHF or UHF depending upon the airplanes, whether it is a commercial or military, different range of frequencies they are using. But air traffic control tower needs to receive all kinds of the frequencies, waves, right, to communicate. Doesn't matter, it's military aircraft or commercial airplanes, they need to communicate. Therefore, they can control the airs. Some of the things that we can hear through our ears I think that is somewhere here, right? I think about this, 10 to the power 4 hertz. That we can hear through our eyes. And this is something that we can see. This is something that we can see. This is something that we can hear. All others we cannot, right? Anybody hear your AM frequency through your ear with no?
Sometimes I hear it.
It will be great if you can hear, for example, cell phone is usually 2.4 gigahertz, right? Somewhere here. So if we go there, then somewhere here, that is your cell phone signals. If my ear is strong enough to capture cell phone signals, then I can hear your cell phones and your cell phones. Okay, the sensors developed in all range. Remember that infrared sensors is widely used. They are using in this range. Some of the sensor, ultraviolet, then that is this. If we are using laser-based sensors, because a laser is a human invented the wave, therefore we can tune anywhere, all around. In the future, if we are thinking of a quantum-based sensors, could be much more stronger and powerful. So sensor that can, I collected some of the video clips you may like. I cannot play all of this, but I will start to play some of those. I put there each how long it is, 16 minutes and 56 minutes. Of course, we cannot do this. How we can make sensors intelligent. And the new approach to sensor and sensing, 15 minutes. And the future sensors using quantum tech, 3 minutes and 59 minutes. So let's try, this is a future for quantum. And then IoT on smartphone. Let's try for that. So
Have you ever wondered how many mobile devices? Mobile devices. Oh, sorry. Just leave it for the end. Just leave
Because
it
we're running out of time, huh?
No. Do you know how many mobile devices are there in the market today? I was doing a research a couple of weeks ago, and I was really impressed that there's 7.1 billion devices, and that number is increasing. If we take the fact that there's 8.1 billion population, and young kids and mainly elderly people is not using, that means some people in this room might be using at least 2 mobile phones. At least I have my Android and iOS. As a developer, we have there. But what we use mobile phones for? Usually we search on the internet, we do some browsing, phone calls. This one less and less, to be honest. We're losing that. We listen music, social media, video calls, at least with elderly people, grandpas and stuff. We take pictures, read books, share documents and pictures, do some banking, some shopping, and even we pay.
Microphones, speakers.
But
yeah.
is that all what we can do with a mobile phone? What if I tell you that we could detect your pose inside this room just using the Wi-Fi signal? Every time, not for this amount of people that is quite huge, but if it's 4 people in a 20 square meters room and you move out, with the Wi-Fi we could be knowing where you are positioning inside that. What if we could do advanced biometrics? How we could do real-time health data tracking of yourself? Or even better, what if I could my physical identity in the network? And using biometrics, I can remove user and password from my favorite applications. Let's say I want to pick money out from a cash machine. I just identify my national ID, it's already embedded in the mobile, and I get my cash out. Even though we have augmented reality modeling, you know, people is now very fan of Cybertrucks, but in Europe it doesn't fit in the garage. So you could scan your garage lot and see if it really fits or not. But we're already doing things like that. For example, I was shopping and getting a unicorn sofa in my home office. So you can place it around and play and see how much it's going to cost. So there are many, many things. And something that a lot of people is talking about nowadays is artificial intelligence. What if we turn our mobile device into our personal assistant? There's a lot of things we can do. And you might be asking, well, gee, where we can start with? This is gonna be our playground. Most mobile phones comes with different sensors, depends on the brand and the manufacturer and how much money you spend. But let's start with accelerometer, no? It measures the accelerometer, the acceleration in the 3/4 dimension. Usually this one helps for step counting, gyroscope, how you rotate, sensor motion, augmented reality. The magnetometer is the compass, so helpful for navigation, maps and stuff. Proximity sensor, nobody writes on this one, but when you call on phone and you drop off the display, just in case you don't touch, that's the proximity sensor helping there. Ambient light, so you don't burn your eyes or you adapt to what's the brightness surrounding. But we have also GPS, navigation, putting the coordinates on your pictures when you take so we can track where you took that picture, for example. Barometer, if you like hiking or climbing, it gives altitude and weather. And LIDAR, which is a laser sensor that hits objects, you get back and it starts drawing 3D maps. So quite useful for augmented reality and other things. And we can use the communication technologies that we have in our mobile phone, like Bluetooth, Wi-Fi, 4G, 5G, 6G that is coming in 2030. And we always use the camera as an input device. Mainly for biometrics, it's going to come really handy. What's our playground today? So this is how it looks. I have my mobile phone and I will share later by the end a QR code that you will see live metrics from my phone. We'll get those sensors, put it out, it's gonna hit an IoT gateway. And we're going to put all that information inside our core platform. You can choose whatever your favorite cloud provider is. In this case, we're using IoT Core, and each sensor is hit into a specific IoT rule. And then I'm going to put all that in a collector called IoT Sitewise. You can do time series database, whatever, and connect it to Grafana. There are a few other things, components in the picture, mainly the Kinesis one. I don't have the integration done on Grafana, but you can embed the video and we could be showing all the people sitting here today with us. How do we start with this? Well, we need mainly 4 things. Connect the device, send the data, collect and do something with it, right? So if we start with connecting, we usually define what we call thing, Internet of Things, to identify a device so we can have serials of attributes already on that. So anytime we define that attribute, we have already pre-populated values that we can just go and fill. But mainly what you need is to create a certificate and a policy. The policy to let us talk to the cloud platform, the certificate to authenticate us. So we create the secure connectivity. Then we need to configure our device, which we're going to do JavaScript on Node.js. I'll show the file now. and then connect over MQTT. The cool thing is that we have 3.11 spec and 5.0, and it doesn't matter if you send on 3.11, receive on 5.0, or send 5.0 with 3.11, it will work handy. Yeah? So, first of all, I want to create with simple command. It's called Grafana.conf. Then you see that's also demo thing. We get an output that is what we're going to use. The thing.
Because ours is not similar to this, so I'm going to skip this. So we're going to, our cloud server is on Google, not AWS. And then here, the phone device that we are considering is iPhone. Connection over is a Mosquito configurations. We don't do this. We could do this from communication from your device to sensor, or vice versa. Sensor is nothing but the Raspberry Pi. Okay. So let's jump. This is AWS. So we don't need to do this. So what I want to do, I want to skip this. The next one is maybe here, right? 3 minutes.
So, how might one harness the power?
So turn off volume. Audio? No? Audio?
Power of quantum physics, nanotechnology, and gravitational research to create nanoscale sensors capable of detecting the elusive quantum gravitational fields. Enter the simplified McGinty equation, or MEQ framework. This ingenious model combines quantum field theory and fractal geometry in a unique way, allowing us to delve into uncharted scientific territory. The journey begins with a clearly defined objective: to develop nanoscale sensors that can detect or measure the effects of quantum gravitational fields. This objective is the guiding star, leading the way through the dense forest of scientific inquiry. The path forward involves applying quantum field theory, represented by PESQFT in the MEQ framework. This step is all about understanding how quantum fields interact at the nanoscale and how these interactions can be detected by the sensors. Theoretical models of quantum gravity effects provide the blueprint for what these sensors are designed to find. Next, the trail leads to the integration of fractal geometry, symbolized by peta fractal in the MEQ equation. The task here is to explore how fractal geometry at the nanoscale can enhance the sensor's sensitivity or specificity to quantum gravitational effects. The fractal parameters, D, M, Q, and S, are keenly tuned to optimize the sensor's design and detection abilities. The adventure continues with mathematical modeling and computational simulation. Advanced mathematical formulation, including calculus and Laplace transforms, are used to create models that blend quantum field theory and fractal geometry. The convolution theorem serves as a bridge, integrating these models to predict how the sensors could detect quantum gravity effects. With these models and theories in hand, the design of quantum gravity sensors comes to life. Simulations predict and optimize the performance of these nanoscale sensors, focusing on their sensitivity and accuracy in detecting quantum gravitational effects. But the journey doesn't end there. Simulation results are analyzed and compared with current technologies to assess their relative efficacy and potential advantages. This analysis fuels the refinement of sensor design, enhancing its ability to accurately detect quantum gravitational effects. The final leg of the journey involves the development and testing of experimental prototypes. Advanced manufacturing techniques, such as electron beam lithography or nanoscale 3D printing, bring the sensor designs from paper to reality. Experiments then test these sensors' ability to detect quantum gravitational effects. comparing the results with theoretical predictions. In the grand scheme of things, this journey may seem like a small step. But in the realm of quantum physics, nanotechnology, and gravitational research, it's a giant leap towards understanding our universe.
I know, we cannot understand all of those, right? But I wanted to simply consider, oh, there is a new technology comes, maybe very quickly. The video, so 59 minutes long, National Physical Lab video, that also very, very useful. We don't, at this point, clearly well understand the quantum physics. We don't really understand the physics itself, classical physics itself. How come we understand the quantum physics, right? I don't expect you to. Me, I don't know either. But at least we need to foresee some possibilities, okay, in front of our future. Okay, let's take a look at each of a few sensors in detail. So let me explain some physics behind. You may be able to. I will do my best to help you. LED. LED stands for light emitting diode, the electronic device that converts electrical energy into light energy. Okay, so electrical is provided. Let's say here plus sign and minus sign. So LED has plus and minus. Usually plus sign is longer. There's two legs, short leg and longer leg. So long leg is usually a positive and shorter leg that is a negative. If you mistakenly opposite this, then your LED may die. It's not exploded. Okay, it's not nuclear bomb. How high voltages comes in here? At the highest, maybe 5 voltages. So 5 voltages, then you don't really hurt any. So LED is so when the power supplied, then some of the electronics combined together, therefore light can be generated. That is how LED works. So LED is essentially a PN junction, positive and negative junctions. In between, there is an opto semiconductor that emits monochromatic, which means each LED generates one color. Okay, light when operated in a forward biased direction. So more clearly, see this is positive and negative. So we have here a positive and negative, where there is a where is it? Negative electric and positive electric charges. So electrically charged here, p-type and n-type. We have p-type and n-type. In between there is a junction. If we supply the power higher and higher, not really higher within the 5 voltages, but anyway power is supplied, then this I think the negative power moves to positive. These two, that is a positive. These two, that is negative. This is negative. So negative electric moves to the positive when there is a positive. So one positive and one negative, they combine together. Therefore, lights generated. Okay. negative and positive together, lights generated.
But as I know now, there's some lights they work with the BOE technology, so the electric will come directly from the internet cable.
I'm not familiar with that. What's a BOE?
The POE like I say there's a line and they have the internet cable called connector, and then when we plug in the internet cable with the Cat6
Okay.
internet cable, then the Cat6 will transfer the energy directly to the line.
Yeah, of course. Yeah, that Ethernet cables,
Yeah, the
the
Ethernet
category
cable.
6, that carries us very light the power energies. So when the line connected, tapped into your Ethernet, the outlets, then your computer will watch that. If there is some data, then there is a little higher voltages, no data, then low voltages. Depending upon that, we capture that, and therefore the network packets can be
Yeah.
identified by your network interface card. But anyway, so it is possible. It's not impossible because there is a power. Okay. So depending upon this, this see here a little bit pink layer, active regions. There's a junction. Depending upon that junction materials, we may have different color. Okay. So if we use gallium arsenide in chemistry is called the GaAs. Depending upon this material, we may have a different color to be generated. So you have a red LED, green, blue, white. I think red LED was first invented. If I remember correctly, it was invented in the college lab, which is Michigan University. So he found out, oh, there's a light can be generated. And then few years later, another guy, by using different materials, oh, we have a green color, oh, we have a blue color, oh, we have a white color. So each different inventors found, it's not, yeah, it is kind of invention, right? So we have this kind of LED physics. So if you see LED, the light can be generated, okay? So 2 legs, then that is called the emitter, and 3 legs, that is called the receiver. So through this emitter, you can send out, and then receiver can receive. So we have, I think this is S for signals, G for ground, and V for the voltages. Through this signal, we can identify, okay, the data. Remember that one of this technology had been used for long in the remote controllers, right? In the remote controller, there's some buttons already designated. So if you push one button, then that button generates some of the voltages, okay? So that's emits that signals. So depending upon that voltages, then at the receiver side, if there is a TV set, then we can say, oh, this is a channel increase or channel decrease, more and more. Okay, with that, LED used infrared, so infrared detection sensors also developed. So infrared detection is nothing but microchips with a photocell. So here photocells that turn to listen to infrared lights. So what this guy says to indicate is that whether there is infrared signals available. Okay, so this guy can detect it. So 3 pins. This is a power supply. This is a ground, and with this pin number 1, we can identify whether there is a infrared waves available. So with the LED, your code is like this. You have to import the time if we use the time, but in this code, time is not used. Oh, here, time.slip. So every 2 seconds, we can switch back and forth, right? So GPIO, RPI.GPIO module needs to be imported. We call that GPIO. So GPIO dot set mode, and look at this, BCM mode. Remember that in your Raspberry Pi, there's a one small card available, and also in the previous slide. No, not previous slide. We don't do yet Raspberry Pi, right? In the future, maybe let me bring up one thing a little earlier. Then there is a this is what I'm talking about. So GPIO, this is a pin, 40 pins available. Remember that here, this is a Raspberry Pi. We have here 40 pins. These pins, each pins, depending upon your mode, if you are using GPIO mode or BCM mode, remember here BCM mode, then BCM mode, then you need to follow this designations. If we're using GPIO board, then you need to simply use pin number 1, 2, 3, 4. This is pin number 1, 2, 3, 4, 5, and the serial numbers. That is GPIO board mode. But if you're using a different mode, which is a BCM, then you need to follow that is a different number, right? GPIO pin number 2 is here. According to board mode, GPIO pin number 2 is this, because this is 1, 2, 3, 4. This is GPIO number 4, but if you are using BCM, then the GPIO 4 is here. This is a GPIO number 4. So back here, if we use BCM, and then GPIO number 4, that's exactly what I'm talking about. Then you need to connect it to here, on left from top, fourth from top. So it should be this red lines. This is 1, 2, 3, 4. That is here. This is a positive, this is negative. Somehow this is not really clear enough, but that is what I am talking about. BCM mode. So GPIO, BCM mode, GPIO number 4, that is out, which means that you are going to supply the power or not. If we say here true, means okay, I want to supply the power. In 2 seconds, okay, I want to cut the power. When there is the power lines, then LED is on. When there is no power, then LED is off. So using this logic, in every 2 seconds, you can turn on and off the lights. Okay, this is for LED. LED, then you need to do wire like this. You need to make a script in Python and run it. Okay, so all other sensors remains the same ways. And the first real technical project is, I already asked you to do a couple of homeworks, right? But real technical homeworks, I think I want you to do this. This is one homework. And then another homework is, I want to ask you to send your data to the server. That is the final step that you have to do. Okay, so that is the LED part. Now we are taking a few more sensor devices to consider. Here, photocells. What photocell is it indicates whether there is a light or not. Okay, so when there is light is shining, then that light goes into squiggly face. This is a squiggly faces, like the tilde face. Okay, something up, something down, something up. So squiggly face, lights shining onto it, depending upon the magnitude of lights, this photocell tells you whether there is a light. Okay. So this photocell is very, very useful in many cases, right? When there is the lights becomes dark, then maybe some of the sensors needs to be get alert, right? In real monitoring systems, your home surveillance systems, when there is no lights, then other sensors needs to be reactivated, right, to watch over that type of things. So depending upon the lights, different actuations, different sensors needs to be activated. So this is the physics behind this photocell sensors. When there is a light is nothing but a wave, photon radiations. So photon radiated, it goes into this squiggly face, and therefore this circuit can be opened and tells you some. So at certain points, if that wavelength in certain points, and immediately then it goes down, therefore it can sense. That's a photocells. Motion sensors. Motion also, there's two types of motion sensors: passive motion sensors and active motion sensors. If it is passive, then this PIR sensor doesn't do anything, right? Only it can detect, it set up the range. If this object comes within this range, then it can detect. Detect by what? Detect by thermal, right? Or what kind of radiations? I think human sensor range, everything emits solar radiation. The hotter something. This is some temperature, right? Thermal wave. When this guy comes in here, some animal comes in here in this range, then thermal waves radiated, emitted, so that emission, that waves can reach this PIR sensor. Some heat comes here, then based upon that, this guy can identify like this. So if you go to this website, gives you the sensor like this. This is the front, this is the back side, and we have 3 pins. This is the same as the one that I showed to you, right? That is this, and this is something that I show. So we have three pins. This is power. This is ground. This power is not to be used to generate or emit the signals to objects. This is power to activate the circuit itself. When the thermal object comes in the range of this sensor monitoring range, then there's a digital outputs. So using that outputs, and of course, you have to calibrate. Somewhere the calibrations. Here, the delay time adjuster, and I think some of the calibrations. Oh yeah, sensitivity adjust. So you can adjust this sensitivity. How quickly that object comes in the range, that is the type of this guy needs to see. And then how quickly that you want to make decisions. How often that you can get this digital signal out, or digital signals to be acquired. So I believe there is this, if you go to this website, then you can find out even some code, the Python codes. Let's see, what is this? This is another, right? Oops, this is not. Let me grab all. See how it works for us. Okay, here. Oh, this is some documents that you can find out. This document probably gives you some of the physics explained. This is the way that you can. This is a calibrator. See here, using your screwdriver, then you can do here. This is a sensitivity. This is, I think, delay time. Power goes here, positive and negative. So positive comes in here. This pin, and this pin may be data. Data maybe here. Let's see, it depends on. Let's see, which pin is for data. Oh, data is in the middle. Yeah, so. So in the this is the data. Data goes in all the way to this LED and here. Okay. Therefore, oh, this is not Raspberry Pi. This is Arduino Uno. See here, Arduino. This is for C language. This is for Python code. This is Python code. But Raspberry Pi, for Raspberry Pi, oh, this is a board. This guy needs to use a board. So a little different, right? Different than my slide. This guy uses a board, not the PCM. It doesn't matter. We can use back and forth. This is different microcontrollers, not our Raspberry Pi. Okay. The different ones here. So in that case, this is so LED 17. You have to import, depending upon the manufacturer, then you need to find out some of the packages to download. This guy is downloaded that motion sensor packages downloaded. And based upon this motion sensor, it checks. The language is a little different. This is not generic Python language, but more provided from this motion sensor packages, these modules. So active motion sense, that this is a passive, right? If it is active, then emission and reflection, those two signals needs to be used. Remember that. So from sensor, the wave needs to be emitted and then reflected, and then receive the reflected waves. So physics behind it uses Doppler effect, time of flights, wave reflections. So we usually think this is much easier than we can think, right? Some of the needs more physics background. Therefore, here in this wave reflections, electromagnetic waves, we use a radar or LiDAR. If it is a radar, then laser signals send out. If it is a oh, this is different. This goes here. Radar, then radio waves. If it is a LiDAR, then laser signals. This is not right. and ultrasonics send out sound. So ultrasonic distance sensor, which is HEC SR04, the website that you can find. So laser, if we use the laser LiDAR, then use different. This, I think this is a very useful ones that you can. Is a clickable? Yeah, that is a clickable.
If we let a speaker make one short burst, we'll create a pulse wave. We can find the speed of sound by looking at the speed of this compressed region as it travels through.
This is about what? Ultrasonic. Yeah, we're talking about ultrasonics. Let's move further. So how ultrasonic, which is this specific model, HEC SR04. So if you go to Amazon.com, HEC SR04 ultrasonic sensors. There are so many different things available, right? HEC SR04, then yeah, this kind of sensors. Two of those, $7 with this cables. Best to sell. This is the sensor that we are talking about. This. So it has 4 pins. So one pin ground, the other pin power, and then one can trigger, which means emit the waves first from these active sensors, and the other one to reflect. We have to receive the reflect sensors. So 2 pins, we need to check the time, and we know what kind of waves goes out. We know that is a sound waves. So what is the speed of sound? There's 340 meter per second, right? This is in classical physics. So if time is 294 microsecond, then distance will be, if this much time elapsed from sending out till receives, then that sound waves travels, it's around the travels, right? It goes out to an object and coming back. So outbound first and inbound. So the time that elapsed, that's a round the trips. So distance is time over to the voltages. This is for the round trips. This is not this is velocities. What is the speed? 340 meter per second. Time is this. So by compute this, then we see the distance between this and that. This is a D. This is simple math. The wirings, you have this SD HEC SR4. So maybe this is the power, this is a ground, and then one trigger and one echo. Then clearly trigger goes here. If we plug here, and then jumper cables from here to this, which is a GPIO 1, 2, 3, 4. I think this GPIO 4, right? If we are using PCM mode. And then echo goes here through this resistance and here, so 1 below that. So this is a GPIO 4, this is 2 below that. That's a GPIO 17. Okay, that is connected. So our code here, trigger is 7. This is not. Oh, this guy used not this PCM mode. Probably used the board mode. So we have to see here. Oh yeah, use the board mode. Because this is a board, the pin number is 17 and 11. If it is a board, then 7 and 11. If we were using PCM mode, then number 4 and 17, right? Depending upon which one that we use. If we use PCM, then we goes this or that. If we're talking about the board, then we need to use these two numbers, 7, 11, or 4, 17, depending on our decision. It's not their decisions. So because of this board, that we use 7 and 11. If we change this to PCM, simply in your code, you have to do this number 4, and this is 17. All others, you don't need to touch. Remember here, this is using, so we get 1 from trigger, get the time difference. After trigger high means we emit. Low means we stop the trigger. So we and then we set that echo, pin echo, get the time 2 times, right? And then get the elapsed time, pulse duration. This is the time for round trip. And then distance, this pulse duration times 17,150, that comes from this calculation. The remains of all, only the change here, this, right? So this is time duration, right? And 1/2 times this sound speed, then this component is fixed. That is nothing but 17,150. I believe, yeah, that is 4 centimeter. If we change this to, for example, the feet, a different unit, then you need to change this. So 30 centimeter is about one foot, right? So you have to divide by this 30. Then you will have a feet. Okay, so this kind of things is a sensor technology that you can capture sensor data. So you have to study on your own, depending upon the sensor, type of sensor. You need to look up the manufacturer's the device specifications, So which pin number that you need to rely on to acquire sensor data. So each sensor has different allocation of the pins. It's not always the way that you can see on this slide. All depends manufacturers and their specifications. So based on that, you need to program it with the Raspberry Pi. The steps that you need to do is very simple. You need to first do proper wiring between your sensor and Raspberry Pi. Wiring first properly, and then codings in Python. Usually the sensor, they have a website to give you code script. You may need to tweak a little bit depending on your preference, and then you can run. As you run, also you may display the sensor data in various different ways, right? So here's the thing. Sensor type, you have to decide whether it is you want to check motion detection, you want to check the distance, or you want to check the photocells, you want to check humidities, do you want to check the temperature, all classical sensors. So you have to decide the type. Once you decide the type, then you need to see which sensor model that you are going to work. Depends on manufacturer, right? Are you going to use, if that is a temperature sensor, then are you going to use active sensor, passive sensor, manufactured by what companies? Then there is a models, right? Type and model. And then you do wiring, scripting, and running. Therefore, you have real values, sensor data. Okay, those three things needs to be captured. And then those three type, model, and data needs to be forwarded to cloud server. Any questions so far? Okay. And then laser-based and quantum-based, those are two things advanced sensor. So next generation precision. So quantum-based sensor leverage quantum mechanics principles, such as, if we say quantum physics, quantum mechanics, then usually three things that you need to three features. Superpositions, entanglement, and then quantum coherent. To achieve ultra precise, not just precise, but it says ultra precise measurement beyond classical sensor capabilities. So I listed here 4 video clips that I chose. This is 60 seconds. This is a little bit funny, and this is good. Talked by Dr. Michael Littman and Charles Eisbell. Only 53 seconds long. It's like TikTok. And then Beginner's Guide to Quantum Computing by Shoni Goes, 10 minutes. She's in University of Calgary, Canada. The other one is Quantum Computing Expert Explains One Concept in 5 Levels of Difficulties by Dr. Talia Gaussian. This is also good. And this is a real lecture. Dr. Scott Aronson. He's currently in University of Texas, Austin. Only reason that he left MIT because MIT has big lab, but he want to make his own lab. But UT Austin provided him, so he developed his lab in UT Austin right now. So this is about 100 minutes long talk. So if you are interested in the future quantum-based sensor or quantum mechanics, then I strongly recommend you follow this. Not all that you can understand. Probably you may understand the 10%, 90% unclear. I want to still watch once more, then you may reduce the uncertainties. Actually, quantum mechanics is based on uncertainties until you finally see, hey, this is it. So it cannot. So what happens is that this quantum mechanics mechanism is very, very strong to communication, secure communications. That is a future technologies. Right now, if you want to keep your data secretly secured, then you have to do a lot, right?
Yeah.
But if you use quantum mechanics, then you don't need to. You can open it. It doesn't tell you until the last minute. So in the middle, that is entanglement. There are lots of wirings, a lot of entanglement. So let's watch some of this. This is real fun. So start with this.
We're
So I think we need to do. I think I need to open this.
Where regular computers base their computations on the behavior of electronic circuits, quantum computers base their computations on the behavior of atoms and photons, often at extremely low temperatures. The weird thing is that these atoms and molecules exist in multiple states.
Hopefully now it works.
Simultaneously, almost like they have twins in parallel realities. And a quantum computer does separate computations in each of these realities. The kicker is that we can only see one of these realities at a time. The real work isn't generating answers. It's making sure you see the reality that contains the correct answer. So, coming back to the example, it's like each domino is both falling and standing, and the probabilities are connected to each other.
That doesn't sound like regular dominoes.
No, they would have to be quantum dominoes.
Quantumos.
Now we understood, right?
Other computers base their computations on the behavior of electronic circuits. Quantum computers base their computations on the behavior of atoms and photons, often at extremely low temperatures. The weird thing is that these atoms and molecules exist in multiple states simultaneously, almost like they have twins in parallel realities. And a quantum computer does separate computations in each of these realities. The kicker is that we can only see one of these realities at a time. The real work isn't generating answers. It's making sure you see the reality that contains the correct answer. So, coming back to the example, it's like each domino is both falling and standing, and the probabilities are connected to each other.
That doesn't sound like regular dominoes.
No, they would have to be quantum dominoes.
Quantumos.
Where regular computers base their computations on the behavior of electronic circuits, quantum computers base their computations
Can
on
you
the
see
behavior of atoms and photons
some of the background
operating at
music?
low temperatures. The weird thing
Anybody
is
know the
that these
background
atoms and
music?
molecules exist in multiple states simultaneously, almost like they have twins in parallel realities.
That's a
And a
piano.
quantum computer does separate computations in each of these realities. The kicker is that we can only see one of these realities at a time. The real work isn't generating answers. It's making sure you see the reality that contains the correct answer. So, coming back to the example, it's like each domino is both falling and standing, and the probabilities are connected to each other.
That doesn't sound like regular dominoes.
No, they would have to be quantum dominoes.
Quantumos.
Hi, my name is Talia Gershon, and I'm a scientist at IBM Research. Today I've been challenged to explain a topic with 5 levels of increasing complexity. It's a completely different kind of computing called quantum computing. Quantum computers approach solving problems in a fundamentally new way, and we hope that by taking this new approach to computation, we'll be able to start exploring some problems that we could never solve any other way. Hopefully by the end of today, everyone can leave this discussion understanding quantum computing at some level.
What's this?
Yeah, what do you think that is?
Fancy chandelier.
I think so too. We jokingly call it the chandelier. That's real gold, you know. This is a quantum computer.
It's a quantum.
Yeah, it's a really special kind of computer.
What does it do?
It calculates things, but in a totally different way to how your computer calculates things. What do you think this is?
A,
Yeah. Do you know what your computer thinks that is?
0, 1.
This really specific combination of zeros and ones. Everything that your computer does, showing you Pink Panther videos on YouTube, calculating things, searching the internet, it does all of that with a really specific combination of zeros and ones, which is crazy, right? That would be like saying your computer only understands these quarters. For each quarter, you need to tell it that you're going to use heads, tails, and you assign it heads or tails. So I can switch between heads and tails, and I can switch the zeros and ones in my computer so that it represents what I want it to represent, like an A. And with quantum computers, we have new rules we get to use too. We can actually spin one of our quarters. So it doesn't have to choose just one or the other.
Can computers help you with your homework, your really hard homework?
Yeah, they can. Especially if doing your homework involves calculating something or finding information. But what if your homework was to discover something totally new? A lot of those discovery questions are much harder to solve using the computers we have today. So the reason we're building these kinds of computers is because we think that maybe one day they're going to do a lot of really important things, like help us understand nature better, maybe help us create new medicines to help people. What's your favorite kind of computer? Smartphone, tablet, regular, laptop, PC?
I've got to go with my iPhone.
So what do you do with your iPhone?
Social media, use it for studying.
Have you ever run out of space on your iPhone?
All the time.
Me too.
Yeah, always when I'm trying to take a photo.
So did you know that there are certain kinds of problems that computers sort of run out of space almost? Like you're trying to solve the problem, and just like how you run out of space on your iPhone when you're trying to take a picture, if you're trying to solve the problem, you just run out of space. And even if you have the world's biggest supercomputer, did you know that can still happen?
Wow.
So my team is working on building new kinds of computers altogether, ones that operate by a totally different set of rules. So do you know what that is?
I have no clue.
It's a quantum computer.
A what?
Have you ever heard of a quantum computer?
I haven't.
Have you ever heard of the word quantum?
No.
Okay, so quantum mechanics is a branch of science, just like any other branch of science. It's a branch of physics. It's the study of things that are either really, really small, really, really well isolated, or really, really cold. And this particular branch of science is something we're using to totally reimagine how computing works. So we're building totally new kinds of computers based on the laws of quantum mechanics. That's what a quantum computer is. I'm going to start by telling you about something called superposition. So I'm going to explain it using this giant penny.
Wow. Is that like worth 100 pennies?
I don't know what it's worth, but I can put it face up, right? And that's heads. I can put it face down, right? So at any given point in time, if I ask you, is my penny heads or tails? Probably you could answer it, right?
Yeah.
Okay. But what if I spin the penny? So let's do it. Okay, so while it's spinning, is it heads or tails?
Heads.
While it's spinning?
I would know.
It's sort of a combination of heads and tails, right? Would you say? So superposition is this idea that my penny is not just either heads or tails. It's in this state which is a combination of heads and tails. And this quantum property is something that we can have in real physical objects in the world. So that's superposition. And the second thing that we'll talk about is called entanglement. So now I'm going to give you a penny. When we use the word entangled in everyday language, what do we mean?
That something's intertwined or...
Exactly, that there's two things that are connected in some way, and usually we can separate them again.
Yeah.
If your hair is tangled or whatever, you can unentangle it, right?
Yeah.
But in the quantum world, when we entangle things, they're really now connected. It's much harder to separate them again. So using the same analogy, we spin our pennies and eventually they both stop, right? And when they stop, it's either heads or tails, right? So in my case, I got tails and you got heads. You see how they're totally disconnected from each other, right? Our pennies in the real world. Now, if our pennies were entangled and we both spun them together, right? When we stop them, if you measured your penny to be a head, I would measure my penny to be a head. And if you measured your penny to be a tails, I would measure my penny to be a tails. If we measured it at exactly the same time, we would still find that they were both exactly correlated.
That's crazy.
It's so cool, right?
Oh my God.
The way that we are able to actually see these quantum properties is by making our quantum chips really cold. So that's what this is all about, actually. This is called a dilution refrigerator, and it's a refrigerator. It doesn't look like a normal refrigerator, right? But it's something that we use. Actually, there's usually a case around it to cool our quantum chips down cold enough that we can create superpositions and we can entangle qubits, and the information isn't lost to the environment.
Like, what could those chips be used to do?
So one of the things that we're trying to use quantum computers to do is simulating chemical bonding. Use a quantum system to model a quantum system.
Yeah, I mean, I'm definitely going to impress all my friends when I tell them about this. They're going to be like, quantum what?
So what do you think that thing is?
Is it some sort of conductor circuit?
That is a really good guess. There's parts of that are definitely about conducting. This is the inside of a quantum computer.
Oh, wow.
Yeah, this whole infrastructure is all about creating levels that get progressively colder as you go from top to bottom down to the quantum chip, which is how we actually control the state of the qubits.
Oh, wow. So when you say colder, you mean like physically colder?
Yeah, physically colder. So room temperature is 300 Kelvin. As you get down all the way to the bottom of the fridge, it's at 10 millikelvin.
Oh, wow.
Yeah. Amanda, what do you study?
So I'm studying computer science, currently a sophomore, and the track that I'm in is the intelligent systems track. Machine learning, artificial intelligence.
You ever heard of quantum computing?
From my understanding, with a quantum computer, rather than using transistors, is using spins. You can have superposition of spins, so different states. More combinations means more memory.
So that's pretty good. So you mentioned superposition, but you can also use other quantum properties like entanglement. Have you heard of entanglement?
I have not.
Okay, so it's this idea that you have two objects, and when you entangle them together, they become connected.
Oh, okay.
And then they're sort of permanently connected to each other, and they behave in ways that are sort of a system now. So superposition is one quantum property that we use. Entanglement is another quantum property, and a third is interference. How much do you know about interference?
Not much.
Okay, so how do noise-canceling headphones work?
They read like ambient wavelengths and then produce like the opposite one to cancel out.
They create interference. So you can have constructive interference and you can have destructive interference. If you have constructive interference, you have amplitudes, wave amplitudes that add, so the signal gets larger. And if you have destructive interference, the amplitudes cancel. By using a property like interference, we can control quantum states and amplify the kinds of signals that that are towards the right answer and then cancel the types of signals that are leading to the wrong answer. So given that you know that we're trying to use superposition, entanglement, and interference for computation, how do you think we built these computers?
I have no idea.
So step one is you need to be able to have an object or physical device, we call it a qubit or quantum bit, that can actually handle those things, can actually be put into superpositions of states. You know, 2 qubit states that you can physically entangle with each other. That's not really trivial, right? Things in our classical world, you can't really entangle things in our classical world so easily. We need to use devices where they can support a quantum state and we can manipulate that quantum state. Atoms, ions, and in our case, superconducting qubits. We make qubits out of superconducting materials.
But as like a programmer, how would quantum computing affect a different way of writing a program?
It's a perfect question. I mean, it's very early for quantum computing, but we're building assembly languages. We're building layers of abstraction that are going to get you to a point as a programmer where you can interchangeably be programming something the way that you already do, and then make calls to a quantum computer so that you can bring it in when it makes sense. We're not envisioning quantum computers completely replacing classical computers anytime soon. We think that quantum computing is going to be used to accelerate the kinds of things that are really hard for classical machines.
So what exactly are some of those problems?
Simulating nature is something that's really hard, because if you take something like modeling atomic bonding and electronic orbital overlap, instead of now writing out a giant summation over many terms, you try and actually mimic the system you're trying to simulate directly on a quantum computer, which we can do for chemistry, and we're looking at ways of doing that for other types of things. There's a lot of exciting research right now in machine learning, trying to use quantum systems to accelerate machine learning problems.
So would it be like in 5 years or 10 years that I would be able to have like one of these sitting in my laptop just in my dorm?
I don't think you're going to have one in your dorm room anytime soon, but you'll have access to one. There's 3 free quantum computers that are all sitting in this lab here that anyone in the world can access through the cloud.
Okay, so quantum computing creates new possibilities and new ways to approach problems that classical computers have difficulty doing.
Couldn't have said it better myself.
So I'm a first-year master's student, and I'm studying machine learning. So it's a computer science department, but it mixes computer science with math and probability and statistics.
So have you come up upon sort of any limits to machine learning?
Certainly, depending on the complexity of your model, then computational speed is one thing.
I have colleagues here that tell me it can take up to weeks to train certain neural networks, right?
Sure, yeah.
And actually, machine learning is one research direction where we're really hoping that we're going to find key parts of the machine learning computation that can be sped up using quantum computing.
Yeah, it's exciting. So in the classical computer, you have all sorts of logical gates that perform operations, and they change an input to some sort of output. But I guess it's not immediately obvious how you do that with quantum computers.
If you think about even just classical information like bits, right? At the end of the day, when you store a bit in your hard drive, there's a magnetic domain and you have a magnetic polarization, right?
Sure.
You can change the magnetization to be pointing up or pointing down, right? Quantum systems, we're still manipulating a device and changing the quantum state of that device. You can imagine if it's a spin, that you can have spin up and spin down, but you can also, if you isolate it enough, you can have a superposition of up and down.
Sure.
So what we do when we try to solve problems with a quantum computer is we encode parts of the problem we're trying to solve into a complex quantum state. And then we manipulate that state to drive it towards what will eventually represent the solution.
So how do we actually encode it to start with?
Yeah, that's a really good question. This actually is a model of the inside of one of our quantum computers.
Okay.
So you need a chip with qubits. Each qubit is a carrier of quantum information, and the way we control the state of that qubit is using microwave pulses. And you send them all the way down these cables, and we've calibrated these microwave pulses so that we know exactly this kind of pulse with this frequency and this duration will put the qubit into superposition, or will flip the state of the qubit from 0 to 1. Or if we apply a microwave pulse between 2 qubits, we can entangle them.
How do we measure?
Yes, exactly, also through microwave signals.
Okay.
The key is to come up with algorithms where the result is deterministic.
Interesting. So what do those algorithms look like?
There's sort of 2 main classes of quantum algorithms. There's algorithms which were developed for decades, right? Things like Shor's algorithm, which is for factoring, Grover's algorithm for unstructured search, and these algorithms were designed assuming that you had a perfect fault-tolerant quantum computer, which is many decades away. So we're currently in a phase where we're exploring what can we do with these near-term quantum computers? And the answer is going to be, well, we need different kinds of algorithms to really even explore that question.
Yeah, certainly having a search algorithm is very useful. Factoring, those are definitely useful things that I would imagine could be done a lot faster on the quantum computer.
Yeah. They also unfortunately require fault tolerance. Right now, the algorithms that we know of today to do those things on a quantum computer require you to have millions of error-corrected qubits. Today we're at like 50, and it's actually amazing that we're at 50. There's things that we know or we have strong reason to believe are going to be faster to do on a quantum computer, and then there's things that we'll discover just by virtue of having one.
Sure. How could someone like me who's a grad student get involved in this, or what kinds of challenges are you facing that someone like me could help out with?
I'm glad you're interested. I think the place where lots of people can get involved right now is by going and trying it out and thinking about what they could do with it. There's a lot of opportunity to find these near-term applications that are only going to be found by trying things out.
I'm a theoretical physicist. I started out in condensed matter theory that studies superconductors and magnets, and I had to learn a new field of quantum optics and apply those ideas. One of the nice things about being a theorist is you get to keep learning new things.
So, Steve, tell me about your research and the work you've been doing in quantum computing.
My main focus right now is quantum error correction and trying to understand this concept of fault tolerance, which everybody thinks they know it when they see it, but nobody in the quantum case can precisely define it.
It's something that we've already figured out for classical computing. Like, something that amazes me is all the parallels between what we're going through now for quantum computing and what we went through for classical computing.
I was asking a computer scientist recently where to read about fault tolerance in classical computing. He said, they don't teach that in computer science classes anymore because the hardware has become so reliable. In a quantum system, when you look at it or make measurements, it can change in a way that's beyond your control. We have the following task. Build a nearly perfect computer out of a whole bunch of imperfect parts.
Common myth. How many qubits do you have? That's the only thing that matters. Or just add more qubits. What's the big deal? Pattern them on your chip.
The great power of a quantum computer is also its Achilles heel, that it's very, very sensitive to perturbations and noise and environmental effects. You're just multiplying your problems if all you're doing is adding qubits.
Exactly. So I think something that frustrates a lot of people about quantum computing is the concept of decoherence, right? You can only keep your information quantum for so long, right? And that limits how many operations you can do in a row before you lose your information.
That's the challenge, I would say. As much progress as we've made, it's a frustration to still be facing it.
Let's talk about some of the things we think need to happen between now and fully fault-tolerant quantum computers to get us to that reality. I mean, there's so many things that need to happen. In my mind, one of the things we need to do is build all these different layers of abstraction that make it easier for programmers to come in and just enter at the ground level. You know?
Yeah, exactly. So I think there's going to be a kind of co-evolution of the hardware and the software up here and the sort of middleware and the whole stack.
Another common myth. In the next 5 years, quantum computing will solve climate change, cancer, right?
Right. In the next 5 years, there'll be tremendous progress in the field, but people really have to understand that we're either at the vacuum tube or transistor stage. We're trying to invent the integrated circuit and scale up. It's still very, very, very early in the development of the field.
One last myth I think we should bust, Steve. Quantum computers are on the verge of breaking into your bank account and breaking the encryption and cryptography.
There does exist an algorithm, Shor's algorithm, which has been proven mathematically that if you had a large enough quantum computer, you could find the prime factors of large numbers, the basis of the RSA encryption. It's the most commonly used thing on the internet. First, we're far away from being able to have a quantum computer big enough to execute Shor's algorithm on that scale. Second, there are plenty of other encryption schemes that don't use factoring. And I don't think anybody has to be concerned at the moment. And in the end, quantum mechanics goes to the side of privacy enhancement. If you have a quantum communication channel, you can encode information and send it through there, and it's provably secure based on the laws of physics.
You know, now that everybody around the world can access a quantum computer through the cloud, people are doing all kinds of cool things. They're building games. We've seen the emergence of quantum games, right? What do you think people want to do with them?
I have no idea what people are going to end up using them for. I mean, if you had gone back 30 years and handed somebody an iPhone, they would have called you a wizard. So things are going to happen that we just can't foresee.
So I hope you enjoyed that foray into the field of quantum computing. I know I've personally enjoyed getting to see quantum computing through other people's eyes, coming at it from all these different levels. This is such an exciting time in the history of quantum computing. Only in the last couple years have real quantum computers become available to everyone around the world. This is the beginning of a many-decade adventure where we'll discover so many things about quantum computing and what it will do. We don't even know all the amazing things it's going to do. And to me, that's the most exciting part.
What do you think? What do you think about the video?
So basically talking the.
So which levels that you think you are in line with?
I think
Professional or
no, I think
elementary?
it's a graduate. So
Graduate levels.
basically talking the normal computer like laptop or personal computer, they are working with 1 and 0. And in quantum computing, they using the spin. It's spin.
Right.
Yeah, not just 1 and 0. So I think that it will be crazy faster than a normal computer for you to calculate any like.
You can simply think. I think you missed the first part that I explained this morning. It's like chemistries. Some of the chemicals, two chemical components, you mix them together, then it's not really 1 or 0, right?
Yeah.
It is somewhere like a pink color, and, then it's like entangled. Right, entanglements. So we don't know what color eventually will become.
Until the end.
Right. So that is exactly what the quantum mechanics is considering, and therefore the world will become different from the world that we live today. We do not know when that world comes, but when it comes, then right, somehow you guys, younger generations, needs to prepare for the future. Don't be surprised. And currently, as I said, NVIDIA, the GPU chips may not be useful anymore. Because it is still relies on 1s or 0s. The future ones is completely different. As you see here, the IBM Q, the quantum computer, it's not anymore the computer that we are thinking, right? It's like remember that initially the elementary school students says, what is that? It's a chandelier. Yeah, it's like a chandelier.
Yeah, so in the future, with a combination of artificial intelligence and quantum computer.
Yeah, artificial intelligence and machine learning will become much faster.
Yeah.
And it's very quick. One thing that I am worrying about, when we have that type of quantum mechanics applied to machine learning technologies, then or artificial intelligence will be really fast, a lot faster than us human. Therefore, human cannot defeat in all aspects. So I'm worrying about that. I don't want to live in that world. But anyway,
big concern about ethical problem.
Yeah.
Yeah. So, but it's interesting.
Okay. I think this is the end of today's lecture. And from next week, we will work on real sensor connections. As I said, wiring, scripting, and running.